Dold on Pseudo-Boolean proof logging for optimal planning.
Thank you for the introduction. I'm presenting joint work with Malte, Helmert, Jakob, Nordström, Gabriele, Röger, and Tanja, Schindler. And from the setting, we are looking at optimal planning. But for just satisfying planning, we are given a planning task, and the output would be a sequence of actions, and we claim that is a plan. Or we say no plan for this task exists. And for the optimal planning case, there we say, oh, the sequence of actions that we are outputting is also a plan with minimal cost. So if we provide a planning algorithm to you, we implicitly give you 3 promises that the produced action sequence is in fact a plan for the task, and for the optimal setting that this plan is also one with the lowest cost. And if we would say no plan exists, then there should actually be no plan. And now we can ask, do we trust those results? And if the question is phrased this way, the answer is obvious. But we can look at other communities, what they do with their solvers. So we can look at the SAT community. They just have Boolean formulas, and they ask, is there a variable assignment that satisfies this formula, yes or no? And they implicitly promise that the variable assignment they spit out is one that satisfies the formula, and in the other case they say, oh, it's an unset formula, and then it actually should be unsatisfiable. And in the SAT competitions, they don't trust those results blindly, but they say they require a certifying algorithm. So that's an algorithm that writes down a proof in a log file that can later be read by a checker to confirm the claim. And this is, evaluated by a checker, and this checker is formally verified. And this way, the checker will only say, oh, the claim is valid if it actually is is indeed valid. So we have more trust in the solutions from those solvers. So how could we do this on planning? If we have the result that an action sequence is a plan, then we already have validators for that, so we could run val or inval. And for the other 2 cases, there was a line of research by Salome Eriksson. So there is an unsolvability certificate for the satisfying planning case, and for optimal planning, there are lower bounds certificates. And we are also tackling lower bound certificates, but we use a different language than this approach. And this allows us to use an established checker, and there we use VaryPB, which is also used in those SAT competitions I mentioned. And with this language, we can argue in a more fine-grained way. So the pipeline of this would be that you as the user have your planning task, and you downloaded a planning system, and you give it the task to the system. And as we all know it, the planning system spits out a plan. And then you could validate it with one of the plan validators. And now the thing that's mentioned by our paper is that we also want the planning system to produce this lower bound certificate. This would then be forwarded to this optimality verifier, which is a third party, so to speak, and that checks that this lower bound certificate is a certificate for a lower bound that matches the plan cost, and that it is a valid proof for the claim that it is a lower bound. So the question is, how can we produce such low bound certificates? And the key insight there is that there is no plan with a cost lower than a given number b if there is a property phi over the state cost pairs that fulfills these three properties. One, this property holds for the initial state with a cost of 0. The second one is that it is inductive under action application. That means whatever you do when the property holds, whatever applicable actions you apply, you can't break the property. And the third bullet point is that the goal state combined with a cost lower than b is not included in this invariant. And if I have this invariant and a proof for these 3 bullet points, then I can be sure that no plan with cost lower than b exists. And this corresponds to a separating set for unsolvability, and for optimality you can think of this as of the nodes as pairs of state and costs, or you could imagine the costs being ingrained into the states. So the idea is that during the search, we write down this representation of phi of our invariant, and we also write down proofs that these 3 properties about the invariant hold. And then after the search, we do the verification, and for that we give an encoding of the planning semantics for the task we are interested in, and this invariant and the proof that we just logged during the search. And then we use this verypb checker to check this proof. And these representation of the invariant and also the proof and the encoding, they are all in this language that verypb understands. And those are 0-1 integer linear programming constraints or pseudo-Boolean constraints. So for the encoding of the planning task, there we do a encoding similar to the SAT encoding, but with a horizon of only 1. So we are given those variables from the task, and we use these for the encoding, but we also use additional variables for the cost, these v subscript c, and with those we encode the cost as a binary number. And then we also have a second pair of these variable sets with a prime, and those are those represent the states in the next time slice. And yeah, for the encoding, we are also using auxiliary variables. So for the representation of the initial state, we just have a conjunction of the facts that are true and those that are false. Similar for the goal condition. And also for each action, we have an auxiliary variable, and we encode it in a way that the variable, if the action variable is true, then all the facts from the precondition have to be true, and all the things from the postcondition have to be true. So in the next time slice, everything from the add effect is true, everything from the delete effect is false, and everything that was not mentioned in the add or delete effect stays the same, so it's the frame axiom. And additionally, the cost changes according to the cost of the action. And this we also encode, this delta c, and here the Pseudo-Boolean encoding really shines, because beforehand everything could have been in this classical Boolean way. But this constraint would have blown up if we would stick to this classical Boolean formulas. And lastly, we have an auxiliary variable that encodes that we are doing some transition, which is just a disjunction over all the actions. And yeah, that was for the encoding of the semantics. And then how do we represent our invariant? For that, we are introducing even more auxiliary variable, and those build some kind of circuit. So R0 is based only on those variables we had in the very beginning, and then we build up new and new variables to build up this one variable that in the end represents our invariant. And with that invariant, we want to prove the three properties I mentioned, and these are also represented in this representable in this pseudo-Boolean way. And the important part here is that here for the inductivity lemma, we have this you can interpret as if you are at a state that's inside this set and you're doing one legal transition, then afterwards in the next time slice you're still in this time in this set, but in the next time step, therefore the prime. But for that to really make sense, we have to have the R phi and R prime phi to be synchronized. So this circuit build-up should be the same. And then so far this was agnostic to the strategy, how we would do planning. But then we looked at a star search, how there we could do it concretely. And there we can express this invariant by looking at all the states that in the end of the search are in the closed set, so those that we expanded. And yeah, for each of them, we have a new auxiliary variable. But also for the states not expanded that are still in the open list, they are still in the open list because their f value was too large, and that is because their h value was too large, and for that we want the heuristic certificate. So we push the problem to the heuristic for now. But if we have those certificates, we can use their invariant and then build our final invariant as a disjunction of the individual state cost pairs from the closed set and the invariants from the states from the open set. And in our paper, we showed that we can do the three proofs for that with a constant factor overhead. So the question is, how does a heuristic certificate look like? And it almost looks the same. The key difference is that we are not starting from the initial state, but from the state we are evaluating, and that the bound is not the final bound, but the h value of this state. And yeah, we have to show the same three lemmas, just that here the numbers are different, and the initial state, sure. And in our paper, we showed that we can also do this efficiently compared to the runtime of computing the heuristic. So with that, I come to the takeaways. So in our paper, we provided a definition and encoding for optimality certificates in planning. And they work by specifying a separating set and showing that this set indeed contains the initial state, but no goal state with a lower cost, and that no action application would lead out of this set. And this can be done efficiently for A star with the Hmax and heuristic and the pattern database heuristic. Thank you.
Any questions?
Yeah, also I have a question regarding the complexity. Also when I generated optimal plans, you have a lot of possibilities to shift around actions. For example, the order of the actions and how you execute it, which are fundamentally equivalent, but it created a huge bottleneck in my planner. Does this occur in your research, and how is it handled, or does it also restrict the amount of plans you evaluate?
I'm not sure if I got it correctly, but this is independent of the order of actions you consider. So if you have a good ordering of your actions, how you consider the successors, that wouldn't change the how efficient the logging would be.
Maybe I can actually restate the question, if I think I understood. Let's say we run A star with partial order reduction, or what do they call this method? Like, stubborn sets or sleep sets or any sort of partial order reduction method, or with symmetry pruning, or any of these other things that can be added on top of A star to make optimal planning have to expand fewer states. How much does this change the proof that you need to output?
Like, we don't consider symmetry pruning. That would require a different proof that we could prune those actions.
Yeah, I mean, the hope with these things is always that with the one proof system, you can efficiently capture all kinds of planning algorithms. And I think the two things you mentioned are pretty much the only things we're a bit skeptical about. Like, I think we can do regression, PDDs, set-based planning, cost partitioning, all the other heuristics. What we don't know how to do is partial order reduction and symmetry elimination. And it's also a challenge for like the set community people we talk to. Like, we try to explain the problem to them and they get very excited. And hopefully in 5 years they get back to us with the answer. But yeah, those are the two really difficult things.
Cool. Mike?
Yeah, wouldn't this apply to any tie-break policy? You know, yes, you're shaking your head. Okay. Done.
Done.
You know, but I mean, the problem with tie-breaking is that there's an incredible number of different ways to break ties. You know, if you look at execution with one tie-break strategy over another, it's just the change in the expansion sequence. You know, and that's really combinatorial.
Yeah, but just changing the order in which you consider the actions, that would not
But
hurt.
that would make something from a solution to a not solution, or it might cause. Are you given the plan?
No,
No.
we are still searching.
What?
They're searching for the plan.
Right. So if you have one expansion sequence, you know, a prefix, you know, a certain, then if you change which, you know, you have this set of tied nodes, you know, and depending on which one of those, it can, you know, go from making it insoluble to expanding lots and lots of nodes. And how do you handle which, you know, so since you could make it insoluble, does that play into how you prove that it's going to be, you know, come up with a solution? I'm not really sure. I'm trying to figure out why these two methods of tie breaking you mentioned are a problem, but other tie breaking strategies are not a problem.
They're not tie-breaking strategies. Symmetry
What?
says you never have to consider the state. You can prune it. That's not tie-breaking, it's pruning. And pruning needs a
Well,
justification.
okay, I'm not sure that I see the distinction between
I
tie
have-
breaking. It means that this node is not the next node I do, you know, expand.
Yeah, but
But-
you put it later in your open list.
Yeah.
And for pruning, you don't put it in the open list at all.
Well, it's at the, yeah, there is a slight, there is, okay, there is a difference, yes.
Like in A star, if there's an F value less in your solution cost, you will not terminate before looking at it.
Right.
So it will be covered. No matter
Okay.
what tie-breaking you do. So this doesn't change the search algorithm. Whatever search algorithm you use, it logs the decisions for the search algorithm and says, okay, therefore it's a proof of optimality. And that proof of optimality can always be done because the search algorithm is optimal.
Right, yes. Okay.